started with last to last class actually started with modeling. Okay, converter modeling. So stepwise we are discussing about the converter modeling. So I told all of you that the purpose of that converter modeling is to represent the nonlinear converter in the mathematically you can describe them. Okay, so mathematically you can describe them to show their to check their dynamics. Okay, basically you know that all are the real-time systems, so you have to represent it mathematically. Okay, so what is the process? So we are normally maintaining some standard process, so state phase averaging method, small signal analysis. Okay, so that's different, that's the conditions. Okay, so that's the conditions and the concepts for it. Okay, so that's why we are discussing different steps of modeling. So as the concern of that steps of modeling, so we are bothered about different on state and off state equations. Okay, so just for that we are taking some examples. Okay, so which converter? So some basic converter like that buck boost converter. So we are taking some examples. So in buck boost converter we can see, okay, so some DC inputs are there. So you know the basic structure of the buck boost converter. So SP single pole double throw, so SPDT switch is also be there. Okay, so in that case you can use some solid state devices. So and your inductor is there, inductor is over here. Okay, so inductor is stored the charge for switch on conditions, when switch is on and when switch is off, so that energy will be transformed from inductor to your load side. Okay, so if you see the concept, so two conditions may be there. One is your on state equation. Okay, another one is your off state equation, and you can see the polarity is plus minus is given here, but normally in buck boost converter the polarity is reverse. Okay, so plus minus like that way. Okay, so in your output voltage is Vt, so Vt, input voltage is Vg. Okay, and your filter capacitor in output side means maintaining that load is fixed, it is by C. So another here we can observe that different switching conditions for when switch is in position 1, that I have told you that MOSFET switch is on. So at this count switch is on means at position 1, so energy is stored from your input side to inductor. Okay, so inductor L. Okay, so that is additional energy stored over here. IT is your current. Okay, so that current, input current, that is coming from Vg to L. Okay, so Vg to L, and that current is there. That current is there. Okay, so here you know that in case of inductor, so inductor current is your state variable. Okay, inductor current is your state variable, and capacitor C is there, and R. Okay, so RC capacitor is there. So here you can observe that C is already charged. Okay, so you can see if it is state 1, so state 0, at state 0 condition that capacitor is already charged. Okay, so which is the equations concept of the state 0. So here you can see state 0 condition. Okay, so capacitor is charged, from that current is coming from your inductor. So current path is like that way. Okay, inductor, that is your inductor current path. Okay, so that is responsible for charging the capacitor. Okay, and the another portion is goes to the load resistance path. Okay, so you can consider like that. Initially it is already charged because you are considered about the steady state condition. Okay, so steady state condition you are considering, so definitely the capacitor is already charged. Your output voltage is your Vt voltage. Okay, so plus minus both are there. Okay, so as per your Vt voltage, so is your output and Vg is your input. So current and the capacitor currents are, okay, so inductor voltage and inductor current and inductor voltage and capacitor currents, you can say like that. So it is a VL, so how much voltage is developed, so that value is VL equal to LDIL dt. Okay, so DIL T. Okay, so T is, why the T is there, so you can consider basically there is two factors. So one is, you can say like the DC component, another one is called very small deviations of that component, so ripple component. Okay, that's why you can say like that it is AC component. So total signal so total signal, you can say like that it is compositions. Okay, so total signal is composited by two signals. Okay, that is your, one is your DC, another one is your AC. Okay, so that's the way. Okay, so that's why you can observe, that your current terminals, you can show that one, that IT. Okay, so what is, you can understand that current is a function of T. Why is it function of T? So that I have explained. Okay, basically that AC component is there. Okay, so AC component means that is ripple component. Okay, your current is not totally fixed DC, so it having some very small deviations or variations of some factors over there. Okay, so if that's why it is time dependent, you can say like that. But normally what happen in the approximated condition, so we are just neglecting them. Okay, so normally we just neglecting that ripples and we can consider it is fixed one, but practically originally some small variations component is always be there. Okay, so it is your IT, and you can see over there, so VG is there, VG is your input voltage. Okay, so what is your IC? So capacitor current. So two state variables are there. So one is your inductor current IL, another one is your capacitor voltage. So I think all of you know about the definition of state variables. So that means you can say like that, the minimal number of variables that having capability to define the state of the system. Okay, that is called state variable. Means if you have lot of energy storing elements, okay, and it's not exactly as per the definition, all that energy all the variables related to the energy storing element is not your state variable. So minimal number of variables, that is represent your system dynamics. Okay, so that is represent your system state. Okay, what kinds of state? Zero condition state means before, that means initial condition state, then how much energy is storing over there and how much energy is dissipating over there. So three state is there. One is initial condition, then charging state, and initially for first your initial condition, then initial state, then due to charging how much state is changed, that is another state. Another condition also be there, after discharging what is your current state. Okay, so three things are most important. Okay, so one is your, you can say like that, IL suffix 0, IL suffix 1. Okay, another one is IL suffix in IL suffix 1, you can say like that, IL suffix 2. Okay, three things are there. Okay, so due to the changing of the state, what is the dynamics? Okay, how much your inductor current or capacitor voltage is changing. Okay, what is the nature of that changing? So normally that's why we are also focused about some of the modeling. Okay, so we are also focused about phase portrait analysis. Phase portrait means, you know that in nonlinear control, I think all of you have gone through it. So what is your phase portrait? Okay, phase portrait means, you can say like that, geometrical trajectory. Okay, so phase portrait is your geometrical trajectories of the dynamics of your system, means of the state variables of your system. If you have two state variable, okay, so that geometric, that axis, you can consider two axes. Okay, so x and y. Okay, two axes will be there. So one state will be considered in your x, one state variable is considered is your x axis, another state variable will be considered in your y axis. So if any of the parameters has changed, you can say like that, your load resistance. Okay, that load resistance, if it has changed with the time, okay, so if it has changed with the time, then what happened? You can observe by changing of your load resistance. So you can see that your inductor current also been changed, also the capacitor voltage also been changed. So every time instant, okay, basically you know that one, that function of t na, so function of time, okay, both the cases it and vt, sorry, both have been the function of time. So all the cases it has been changing, okay, and you have to fetch for the every instant of the time that value, okay, values of inductor current and capacitor voltage. After that, what happen, you have to plot those values, okay. After plotting those values, so you are getting, so xy coordinate Cartesian method, no, so you are considering like that Cartesian method. So in x-axis you know that coordinate of that point is x comma y, okay. So in x-axis you are considering one state variable, in y-axis you are also considering another state variable. So x comma y means for every instant that inductor current and the capacitor voltage, okay. So you can plot every instant that value, okay. So time is not there in any of the axis, but you know that after changing of the regular interval of time, okay, so there should be regular interval of time changing. If that irregular means first you are taking the value as 1 second, then you are taking it 2 second, then 3 second, like that, it is correct manner. If it is, if your system is much more sophisticated, you can segregate the time scale, okay. So 0 to 1 second you are also considering another 10 points, okay. So 0.1 second, okay. So 0.1 into 10, it is your 1 second. Then point after 1 second it will be 1.1 second, then 1.2 second, up to 2. So equal regular intervals, okay. You should not take any irregular interval. Irregular interval means again non-linearity will be there, okay. Means what do you mean by irregular interval? First you are taking the results for your system 1 second, then you are taking 2 second, since suddenly you are taking 4 second, then 5 second, it is irregular interval. So you should not take it like that way. So as per consideration, your time scale is a linear changing, okay, linearly changing, like that, okay. For every instant you are taking the same interval of time and you are measuring that value. So all those coordinates you will get, now you have to connect them, okay. So connect them, so after that you are getting the portrait, that I am telling you, geometrical structure of that attractors, okay. Attractors means that's the trajectory part, okay. So trajectory part we will get, okay. So you can see it's a state phase modeling, you can say like that. So you can understand the dynamics of the converter. So what are the dynamics, how do you physically realize it? So you know that in nonlinear control it was there like that, your repeller structure, okay, attractor structure, you know that limit cycle structure, okay. So I think all of you have remembered all those things, okay. So it was in your 6th semester control systems, okay. So some different, so what do you mean by the saddle, okay, what is node, then what is your limit cycle, the definitions of the limit cycles, okay. Then if that values of r is changing, so again that limit cycle periodicity also may be changed, okay. So limit cycle is not your transient behavior, definitely it is a steady state behavior, and limit cycle having fixed periods, okay, for individual parameters. So I think all of you know about your that is not Lyapunov equations, it is Van der Pol equations, okay. Van der Pol equations, okay. So Van der Pol equations is an example of that limit cycle. So power electronics converter, the switching converters, why that is switch, we are much more bothered about these kinds of non-linearities, okay. Basically switching converter having inherent non-linear property that I discussed so many times, okay. Switching non-linearities, okay. That's why these dynamics also very important, okay. So in normal conventional power electronics we are not focused about such kinds of dynamics, but when we are going to be studied about it, so we have to know their nature, dynamic natures. So based on their dynamic nature we have to design the controller. So arbitrarily we are not going to design any of the controller, okay. So definitely there should be one motivations. Okay, so why we are selecting that classical controllers? Means classical means you can select that P controller, PI controller, lead controller, lag controller, lead lag controller, lag lead controller. Okay, then we are also using some K factor based controller, means PI plus lead controller, PI plus lead controller. What is that motivation? So why we are discussing such kinds of classical controller. Also we are also designing some nonlinear controllers also, like that I am telling you, na, geometrical attractor based, okay, trajectory based controller. You know that one term is very popular right now: sliding mode controller, predictive controller, Kalman filter based controller. So a lot of controller also be there, but which one is perfect, which one is suitable for our specific converter, that is most important. So how do we get that kinds of thing? That's the modeling, that here we are getting the expression of that state variables. Okay, so we have to know about it. In this case you can see it's, I am taking very simple converter like buck boost converter. Okay, so buck boost having boost, buck and buck boost. Okay, then you can go for that tube converter, sepik converter, that is different. But in up to these three conventional converter having two energy storing elements, so it having only two state variables. Okay, so if we get the roots of the system, so you can see that the quadratic equation you are getting over there from the differential equation, so you can understand it having second order system. It's an example of a second order system. So two sets of equations will be there, only two roots are there. But if you introduce more energy storing element like tube converter, zeta converter, okay, so in the sepik converter, in that case you can see it having more than two order. Okay, means tube converter, four energy storing element. Okay, so fourth order equations. Okay, so when you are plotting the dynamics, so definitely it will be different with your boost converter, buck converter. And after checking the converter basic dynamics, you can select the controllers. Okay, so is it capable, if that dynamics is controlling by the classical controller? So if there any kinds of problem, so if there is no problem, you should go for the classical controller. That will be coming from my other classes. Basically what happened in this year, the time is very short and we have to cover lot of things. Okay, so that's why we are asking for more classes. So if we take more classes, we can share my ideas, more ideas with you. Okay, basically all the times you are not getting such kinds of scopes. Okay, so basically it's a very beautiful subject, and I am not try to bounded that syllabus within that the syllabus of any other conventional book. So some of the other things we can also I am also trying to discuss that is beyond your syllabus, means beyond the book syllabus. Definitely in post graduations means what, you are definitely much more closer to the research. Okay, no, so some additional idea I want to share with you. So in switching converters, okay, so that is that theory is not written in any books. Okay, so that's why I am asking for more classes. That's the basic motivations. Okay, so you know more thing about that switching mode converter. Basically you don't know that after complete that actually this, that is only one single subject. Okay, so all the time what happened, so after completing your post graduation, some of you are more interested to do PSU job. Okay, some of the students also interested to go for the teaching job. Some of you are also interested for doing your further studies like your PhD, any of the foreign universities. Okay, so or in IITs. Okay, so reputed institutes. Okay, not like a reputed institute in India means IITs, then top NITs like NIT Rourkela. Okay, so all of you having different dream. Okay, so we have to prepare the syllabus that should contain the concept of such as bookish knowledge, as well as some of the concept is not covered by the book. That's the basic motivation. So basically right now that all the classes in virtual mode, so if it is happened in the class, so it will be much more better. Okay, but what we can do in this pandemic era? Okay, So that's why I'm trying to my giving best. Okay, so some of also covered some of the topics based on that converter dynamics. If you have some time, okay. So normally I'm taking for 3 credit subjects minimum 30, minimum 42 classes. I don't know this semester what happened. Okay, so basically we got instruction in last means yesterday, so we have to complete the syllabus as early as possible with taking some additional classes. Okay, so we have to reach that amount. So normally 3 credit subjects means 30 classes, the normal conventions. Okay, if the classes are in physical mode. Okay, but if it is virtual mode, we can consider maybe minimum 35 classes is there. But normally in my cases, I am in average I am taking 42 classes when it is happened in the physical mode. So I just think about it. I can take at least 40 classes. Okay, so that will be better for, definitely better for students. Not actually I want always be there for share my knowledge. Okay, but some constant is there in this semester. The time constant is there, but we have to cope up, or we have to adjust. Okay, so it's a collaborative, so it's a teaching learning process. Okay, so teachers sometimes also learn from students, students also learn from teachers. So basically in this cases, so it's a teaching learning process. So both of the side, they can learn and they can enrich their ideas. Okay, some ideas you can also float. Okay, so I don't know that is we can manage for mini project or not. Time is not, I think we are not getting much more time for it. Okay, but still we should try. Okay, okay, so I am not expend means more time on that discussions. Okay, so I should come back to our main slide. So that's why we are and we are taking some example for a buck boost converter. Okay, so here we can see that in inductor voltage is there. So inductor voltage you have to calculate. So for switch on condition, that voltage directly it is your input voltage. And what is your in current? So capacitor current. So if you calculate by using KVL, so you can easily find out that value will be minus Vt by R. So why it is function of T? I think right now all of you will be able to understand. Okay, so if you plot the dynamics, so initially it will oscillating. So if you see the step response, time response, phase portrait is not your time response. Okay, time is there, one axis is there, time, but you should calculate in back of the mind. Okay, the time axis is there, but basically phase portrait done by one axis is your one state variable, another axis is your another state variable. But step response, if you see, it's a time domain analysis, totally time domain analysis. In x-axis you have time axis, okay, and y-axis you can say like that one of your state variable. Okay, so like that way. Okay, so if you see initially if it is, what happened?
Slide is not changing.
No, I am not changing the slides. Okay, so the slide is fixed, same slide is there. Okay, so so what happened if you see that critically damped condition? Okay, so initially some oscillations are there. Okay, so due to that oscillations, okay, you can see that attractors. Okay, so that attractor. So in my next week, you all of you try to simulate one buck converter, so on buck converter or buck boost converter. Better you can go for that buck converter first and boost converter. Okay, so write down the state equations and try to simulate through try to simulate in MATLAB. Okay, so don't use you can use any of the conventions. Okay, like state variable approach you can also use, or you can also use some transfer function based model. Okay, and show me the response. Okay, so next week I will also ask. Okay, so all of you please share your scheme. So I want to check the response of buck converter and boost converter and the response of their state variables. Okay, like buck converter, that inductor current and capacitor voltage, what is their response in XY plot, and in boost converter the same thing I want to see. And if you change the variable with regular interval, so what is their dynamics, what is the changing of the dynamics in x-axis in xy axis. So that you have to be studied. Okay, so that portion you can do it in your home. Okay, so that is your another assignment. Okay, so show me that results. Okay, so you prepare one office file. Okay, so all those results should be there, and you can send it to me at the form of assignments. Okay, so I can check, I can see that how much you can observe from that simulations. Okay, so what is the dynamics? Okay, what is that value? Eigen values are there. Okay, so if you change that value of resistance R, so how that eigen values are changing. Okay, so you can also plot that eigen value with the value variable. You can use some for loop. Okay, so by changing that value of R, how that eigen value is changing. So you can placed over here. Eigen values are changing and the inductor current for individual instant. Okay, you are changing the value of R. So at time equals to 1 second, you will get some of the inductor value and the inductor current value, some of the capacitor voltage value when time is to some changing. So you can plot some diagram that your R is changing and time is also changing with regular interval. For individual instant, you are fetching the value of inductor current and that capacitor voltage and plot them with the respect of changing of your resistance. Okay, that is your assignment. So next week you can show me that results. Okay, so I can check it. Okay, so here you can see the state equations. So state equations where your output voltage by R, it is your current. So we are using KVL. So now we can approximate that ripple values and replace the waveforms of the low frequency average value. So I told you that we are approximated it. So low frequency ripple we can calculate it. Sorry, we can neglect it. Finally, we will get that inductor voltage is your average voltage and with your total period of time, that is your TS time. And what is your IC? We can also observe the value of IC. So it is C dVt dt, and finally you can approximate that value. So your that is your mean value. Okay, so it is average value. So in the rest total period of time. Okay, so that is your output value. So Vt within that mean value by R. Okay, so in switch to positions, so now right now we have changing that positions. Okay, so in switch to means position 2, when switch is off, you can say like that. At switch off condition, you can see that inductor voltage and capacitor current. Okay, the nature of inductor voltage and capacitor current. Okay, so what is the response of inductor voltage? VL, it is L d I t dt. Okay, so it is similar to your like one. So first case both are same. Okay, so inductor voltage is your output voltage. Okay, basically switch off means your input voltage is out of the circuit. Okay, so it is open. Now your inductor voltage VL equals to what is your parallel, that output voltage, it is your Vt. Okay, inductor voltage is parallel with your Vt and it is your inductor current. And capacitor current IC equal to what, your inductor current plus inductor current equal to capacitor current plus output current. Okay, so you can say like that. I am telling you that in back boost converter that convention is reverse, so it is practically it is minus, it is plus. So that's why they are putting that all the things are minus. Okay, so minus IT is in inductor current. Okay, so IT equal to what? IT equal to IC plus I0. Okay, I0 means load side current. So you can see like that. So IC equal to minus IT minus I0. So you can replace those value. Okay, so minus IT minus BT by R. Okay, so you can neglect the ripple, you can neglect the ripples. Okay, so from your signal, and finally you can get that approximated value, and you can omit that low frequency value. And what is your low frequency, omitting low frequency average value? So how much value is there? So you can get that VL equal to that LDITT. So that value will also be averaged over the total switching period. Okay, so your inductor capacitor currents also be there, or it will be again averaged. Okay, so over the time period. Okay, so switching time period. Okay, so you will replace them and you can neglect all those ripples, okay, high frequency ripples. So after getting all those equation, now we can go for average inductor waveform. So you have that inductor waveform means VL waveform. So you know that first condition energy stored and second condition energy is discharge. Okay, so that's why condition one you will get some positive half, and in second case you will get some negative half. But practically that if you follow the dotted line, okay, so dotted line means it is your average line. So if you neglecting the ripples, okay, so you know that initially that some inclined, okay, so some inclined is there, inclined is there from it is not equal parallel to your time axis. Okay, it is your time axis, it is not parallel, so it is gradually increasing both the cases. Okay, positive half as well as negative half gradually increasing both the cases, here gradually increasing, here gradually decreasing. Okay, but if you go for that average, so you can see some dotted line. Okay, so some dotted line means that average line you can observe over here. Okay, so that dotted line means you are getting some average. Okay, that is parallel to your time axis. Okay, so that dotted line means for your TS. Okay, so period, time period. So DTS means is your on period and TS is your total switching time instant. So what is your off period? TS minus DTS. Okay, so what is that expression that you are getting from that equations? Okay, so that inductor voltage waveform. First, you are considering about that inductor voltage waveform. So, what is your expression? That low frequency average is found with the equations of XL. That it is one of the state variables. So XLT with the time period of TS. So 1 by TS, T2, T plus TS. So XT, X tau, D tau. Okay, so state transition matrix. Now, so average inductor voltage, if you are now making it average, so finally you will get the expression like that, that dt is there, and simple thing, dt is there, then Vg you can replace that value of VL. So what is that VL? VL equals to is your Vt. Okay, so Vt, and see what is the value of VL. VL equal to VGT, okay, for into T, and VT plus VT into 1 minus DT. So if you replace all of them, so finally you can say like that DT is in stands for what? DT stands for on time. Okay, so duty ratio for your on time, and D dash T means duty ratio for your off time. So on time condition, you are getting that what type of value? So you are getting that input voltage, so VGT. So that's why the what is the average value of VL? Okay, so VL equals to, you can say like that, D dash, sorry, DT. DT means when switch is on, so that condition, small d t. Okay, so small d t s. So small d is a function of t, that's why it is written like that dt. Okay, and multiplied with your input voltage for your switch on condition, and it is definitely averaged in your switching time period. And in switch off condition, what value you are observe, that is your VT. VT means output voltage. So that D dash term is there due to switch off condition. So here you can see that switch off condition, you will get the means position 2 when switch is in your position 2. So you will get the expression VLT equals to VT. Okay. So you are average that value of VT over the switching instant, over the switching period. Okay. So now we will get that expressions. Okay, so VL tau into d tau, okay, equal to dt within brackets, so VGT TS plus d dash t within means average mean value, so VT TS. Okay, so now what is your expressions of inductor current? So we are following that Ericsson book, that's why that equations I am directly taking from Ericsson book. So you can follow that book, so for that better better clarifications, better ideas. Okay, so here we can use that inductor current. So right now you just replace them. XLT means it is in state variable form. So right, you can elaborate that one. So you will get some derivative form differential equation. So L d di within bracket dSdt equal to dt Vg t into Ts. Okay, so that equation describes how the low frequency component on the inductor waveform evolve in the time. Okay, so you can say like that, that is showing lot of mathematics here. Don't be confused over it. Basically switching converter is a physical system. Okay, when you are mathematically represent them, so that's why some of the mathematics is there. So don't be worried about it. This is very simple thing. Okay, so there is no such any complicated one. Okay, so try to be realize the thing, try to be realize the problem, that is most important. Okay, so now what is the we can observe over here, what is the basic discussions for averaging approximations. Okay, so basic discussions means here you can see inductor voltage waveform. Okay, so you can see gradually increasing that inductor voltage, so that may cause for, I told you na. So see, inductor current is your one of the state variables, so I0, but I am told you that is not the transient response, it is steady state response. So as steady state, definitely it having some fixed value of current, so that is your I0. So it is starting with your I0, then gradually increasing, and it is go with the slope of that slope is already given, that VGTS by L. Okay, that expression of current. Okay, so what is the expression of current for on state? That is L DIL dt equal to Vg. Okay, so what is that slope of that current, inductor current? DIL dt equal to Vg by L. Okay, for on state means when switch is on, so Vg by L, and when switch is off, that is coming that Vt by L. Okay, so the slope means first it is charging slope, charging current of your inductor, it is discharging current of your inductor. Okay, so discharging current slope is output voltage by inductor voltage, and charging current is that is slope of charging current of inductor is input voltage by inductor. So that is written over here. So VGTS, okay, average value, that's why within greater than and less than block, and suffix is ts, and it is by L, and slope is VTS by L. Okay, that output voltage over the period. Okay, so we'll get that one. Okay, so what we can conclude from the discussion, what we can observe over here, the use of average inductor voltage allow to us determine the net change in inductor current over one switching period. That is most important. So net change of inductor current, you can see over there, zero state, I0 state to IDTS means on time state, then on time state to ITS means up to off time state. Okay, means it is your final switching pulse. Okay, final switching time period. This is on time, this is your off time, the duration is your off time. So in between DTS to TS, so that is off time, and on time is 0 to DTS. Okay, so so you can understand that inductor voltage and current waveform, so you are getting some steady state response, and while neglecting the switching ripples, and you are also neglecting the switching ripples. Okay, so that's why the dotted lines are there. Okay, so dotted line stands for the neglecting the ripples, and here you will get some average value. Okay, so that expression, it is totally dotted line, it is not exactly zero. Okay, nearer to the zero but not exactly zero. Basically why it is not exactly zero, if both positive and negative cycle, okay, so both positive and the negative cycle of inductor voltage is equal. Okay, so that amplitude means area. Okay, so you can say like that, energy storing and energy relieving. Okay, so both are same definitely as per the convention of that one. So that's why average value should be 0. Okay, as per the convention, but it having very less bias value. Okay, so that's why it is written that nearer to, you can see that one, that is nearer to 0. Okay, that value is nearer to the 0, not exact to the 0. Okay, in steady state condition, okay, the average inductor voltage is 0. Okay, that I am told you na, voltage second balance. Okay, that energy, and hence the inductor current waveform is periodic. So IT plus TS equal to IT. Okay, so IT plus TS T plus Ts equals to It. So there is no net change in inductor current over one switching period. Okay, so during transient or AC variant, the average inductor voltage is not zero. Okay, in general, and this lead to net variations of inductor current. Okay, so you can see, I think you can see, and you can understand that idea. So net variation of inductor current is what? Zero. Okay, so average is definitely you are making it average, and so definitely it will be zero. So what is your net charge? So first one is your inductor voltage waveform. Now you can say like that inductor equations, you know that equations. Okay, so I d L d I L dt equal to VL. So here we are discussing about net charge in inductor current. Okay, so predictions. Okay, so what is the predictable inductor current for the next instant? Means up to Ts you can calculate it. Okay, zero condition, then dTs, then only Ts. So three instant you can calculate it. So what will be the next one? So what you can go for the prediction? Okay, so if it is nth cycle you can able to calculate. So what is the prediction of n plus 1 cycle, and what is the prediction of n minus 1 cycle? Okay, so one cycle is already you have calculated. So what is the prediction for the next coming cycle, and what is the prediction for your previous cycle? Okay, so that you have to calculate. So divide that L in the one switching period. So you know that expression that I have already told in my last slide. So then you can see like that. It will be like that. What is that amount of charge? Okay, stored over here. So IT plus Ts. Okay, so next instant, and it is your Tth instant. Okay, if you subtract both of them, so that energy will be stored in the inductor. Okay, over the time period. Okay, so that is the convention of this theory. Okay, so left hand side the change of the inductor current, and right hand side is the related average inductor voltage multiplying with it, multiplying and dividing by the Ts follow. So you know that values of inductor time period. Okay, so inductor current, inductor voltage over the time period. Okay, so you can multiply both of them and divide it by Ts. So finally we will get that expressions. So the net charge in the inductor current over one cycle or over one switching period is exactly equal to the period of Ts multiplied with the average slope. So definitely, so you can see like that one slope is there. Okay, so you can say like that Ts is multiplied with the average slope. So what is your average slope? So average, the expression of VL is like that, what? VL equal to Vg into dTs plus Vt into d dash Ts, okay, whole divided by Ts, okay, into 1 by L. So that is the conventions. Okay, so directly exactly that value of that multiplied with your average slope. The Ts is multiplied with your average slope. So average inductor voltage. Okay, so correctly predict the average slope of ILT. So you know that on time slope, that is your Vg by T divided by L. Okay, it is your on time slope. So actual waveform including the ripple. Okay, that is your actual waveform including a charging condition, then discharging condition. It is coming over there. So what is your I0? I0 is the steady state current that is starting from there, initial condition. So I0 and ITS all are in the same line. Okay, so all are in the same line. Sometimes it what happen, I0 and ITS is not in the same time. It's also happened. So when it is happened, then you can see the periodicity of the state variable or the periodicity of that phase portrait, okay, has changed. Okay, so if both are in the, if both are not in the same line, that line is parallel to your time axis. If both are in not the same line, then that periodicity has changed. Okay, so if I have some time, okay, after completing all those things, so definitely I will show examples with diagram. Okay, where that initial current condition and that final current inductor current condition are not in same line. Okay, so that is indifferent. Okay, so after some period it is coming to the I0, means same line. Okay, so how that changing is there. Okay, and what is the dynamics, what kinds of dynamics is change over here, that we can observe from the study. Okay, so here you can see it's your current expression, and dts is there. Okay, so dts and ts, that on time current is there, how much current is stored from initial condition to final point, and final to up to total value. So total value means total time period. So current is rise up, then it is be rise down through the slopes. And what is the dotted line? Dotted line is your average waveform. Okay, after getting all those things, so you have to make it, the average value. So it dotted line is your average waveform. Okay, it is your average waveform. Okay, so it with over full the cycle, and ts is there. Okay, so you are getting that one, and that value, you know, that one that I'm telling you here, that vl, that inductor voltage over the cycle, over the switching period, all divided by L is your the average value. So here you can calculate that value. So D into Vg within Ts. So multiply it with your duty. Okay, so and it is D dash. Okay, so it is on time. Okay, so on time slope. Okay, so it is L. Okay, on time slope plus off time slope. If we add both of them, so you will get that average value. Okay, if you divide it by Ts, then what happens? Then all the things. So okay, so what the, so you will get the exact average value. Okay, that's the convention. The net charge in inductor current over one switching period is exactly equal to the period of Ts multiplied with the average slope. Okay, so that is VL within bracket Ts divided by L. Okay, I think till now all of you have understand what I am going to discuss with you. Okay, I think if you don't have any kinds of confusion, if you have any confusion, please tell me, so again I will discuss it. So do you have any kinds of confusion? Please tell me. Am I audible?
Yes, sir.
Is there any confusion? All of you able to understand what I am going to discuss? So please tell me if you have any confusion. So again I will discuss some portion. Is there any kind of confusion?
No, sir.
Okay, so I think there is no confusion from your end. So here you can see that we can write down that equations. Okay, so if it is your switch, ITS means your up to current up to switching instant. Okay, so it is your current up to switching instant. So means switching period. Okay, so we can predict. Okay, so over the switching cycle. Okay, means after ts definitely there will be some cycle, so we are considering t instant. Okay, so definitely current will be changed from its plus t, so that's why its plus t is there, so minus it. So how much values will be there? So it is coming, the slope is directly coming from that formulas, that one, that formulas is there. Okay, it plus ts minus it equals to 1 by l ts within bracket means mean value of VLT. Okay, so we can replace that value that I have already discussed how we are getting that value. Okay, so time instant whole divided by that multiplications. Okay, L will be multiplied over here, and that TS cross multiplication, that numerator term. Okay, so that denominator term, if you cross multiply it over there, it will come to the numerator L, and TS is your numerator. Right now it is come to the denominator. So that value VL within bracket T in the over the average value, it is Ts. Okay, so now define the derivative of ITS as the Euler formula. So Euler formula means, you know, that very popular formula. Okay, so numerical analysis. Okay, so you can use any of the differential method. Okay, so means integrations actually. Okay, so you are using any of the any of the methods. So directly you can get that value. Okay, so in average value that I am told you is that DIL dt. Okay, na DIL dt. So dt value means your over the cycle value TS. Okay, IT plus TS minus IT whole divided by TS. So hence you know that value L di dt di over the TS means switching period equal to VL T over the TS. Okay, so same formula we are also using for computing how the inductor current change over one switching period. Okay, so that we are also going to be compute. Okay, so I0 is there. Okay, I0 is there, ITS is there, and IDTS. Okay, so this instant for on period, this for off period. Okay, so VGTS by L, VETS by L. Okay, all are there. Okay, so finally we can check. Okay, so finally we can check up to 0 to DTS, that on time, then up to off time. Okay, so finally we can check it for the position 1. Okay, so position 1, that value is IDTS equal to final value equal to I0 plus DTS for length of interval. Okay, into length of interval into the slope, average slope. It is your VG T whole divided by L into TS. Simple thing. So if you write down the expression of state equations, okay, sorry, state line equation, okay, y equal to mx plus c. Simple thing. Okay, so write down that equations y equal to mx plus c. Y, that y is your what? That I y equal to mx plus t. Na? So m into x, what is your m? Gradient, that is your gradient. Okay, so vgts whole divided by l into t, not ts into multiply is not there, it is suffix. Okay, means you are write down the gradient. Mx, what is your, that is your m. Okay, slope is your m. What is your x? X is 0 to t dts. So dts minus 0 means only dts, so it is your x. So m is there, x is there. Okay, so plus c, y equal to mx plus c. What is your c? It is your I0. What is your y? Y is your I. On time you are getting the current, you are find out for that on time, so that I dts. Okay, that you are going to find out, that I dts. So second condition. Okay, for when the switch is in your position 2, here you have written the switch is your position 1, switch is position 2. So what is that formula? Y equal to again mx plus c. Okay, so what is your y? Y will be ITS, that is your final value of current, that is your y. Okay, mx, what is your m? M is your off time switching slope is V, means output voltage. Okay, average over the switching instant, that is TS, or switching time. Okay, not instant, it will be switching time over the switching period. Okay, not over the switching instant. Okay, instant is not the correct word, over the switching period. Okay, that is VTS by L. Okay, so VT over the cycle TS by L is there. Okay, and what is your output voltage? So D dash T. Okay, D dash T means is your off time length of interval. It is your off time length of interval, that TS minus DTS. It is equal to D dash TS. So what is the value of D dash? It is 1 minus T. Okay, so you can subtract the TS minus DTS. So TS is common, within bracket 1 minus T. So 1 minus D term you can say like that, it is D dash. Okay, so that is your mx term is there. Okay, y, then c, what equal to mx plus c. C term is your dts. So what is your instant? So it is your dts, na. So that c terminal is I into dts. Okay, that value is here, that c component over there. Here it was I0. So I think you know that value. So final value equal to initial value to length of the interval very slow. But where do you get this expression? The expression is coming from y equal to mx plus c. So here you are considering that linear ripple is approximated. Okay, linear ripples are approximated. Now we can add them, add both of them. So what is that value? So net change of inductor current over one switching period. Okay, so we are adding them. So eliminate that IDS to express in ITS. So you know that value of IDS. So IDS, that value, that IDS. Okay, it is your IDS. So now your that IDS value, okay, now you are replacing that IDS value over here. Okay, so now you are replacing that value IDS. So finally you will get that expression of ITS. So what is your ITS? So it is your ITS. Now you are going to calculate the value of ITS. Okay, so what is that expression? So I0 plus Ts by L dt Vgt into suffix Ts. Okay, so suffix Ts is there, d dash T Vtt, that suffix again Ts. So it is here. Finally, you can say like that VLT over the time period. Okay, the average value of inductor voltage. Okay, so actual waveform, you are getting that actual waveform including the ripple. Okay, so that actual waveform. So I think you are able to understand. So that was there. Okay, actual waveform means that actual waveform, that actual slope is there for the on period, slope is there for the off period, and you are getting that average value. Okay, so all the things is there. Okay, so all the thing I think you are able to understand. How would I get that average waveform? Okay, and what is that actual waveform with the ripple? Okay, so how that expression is coming? Okay, so that expression you are getting from here. Okay, so Ts whole divided by L. Okay, and I0 is your initial value, that C value. Okay, I think all of you till now you should not having any doubt. Basically, it's only the mathematics. Basically, very simple equations of straight line. Okay, so I hope all of you can understand. Okay, and you can go through or you can read it from Erickson book. So that is given in the chapter 7. Okay, so you can follow from there also. Okay, so Erickson book is very good book. So you can follow that book for any of your course purpose. So Erickson book is not totally for switch mode power converters. So some of the portion is matching with that syllabus of SMPC, but if you go through the total book, so you have ample idea, okay, a good amount of knowledge, a good idea knowledge from power electronics converters, advanced power electronics converters, and switching converters. So total thing, and the control also, how to design the controller for the switching converter. It's a very good books, you can follow from there. And another very good books also be there, that is your Ned Mohan books. Okay, so Ned Mohan books, it also very good book. Okay, but I think it is I don't exactly remember the part number. It having only single volume book. Okay, Ned Mohan book also single volume book. So one chapters are there starting from switch mode power supplies. You can follow the theory from those points. Okay, so it is also very good book. You can follow the switching methods, you can follow the mathematical approximations. Okay, what we are the normal methods for modelings of the switch mode power converters, everything is also discussed over there in Neil Mohan books. Okay, you can also follow the Philip T. Crane books. Okay, a lot of books are there. Okay, so Crane books having another good approach, but the thorough modeling, everything is given better in Erickson book. But sometimes some theory. Okay, so one of the author, different author having different philosophy. Okay, some of the author they are much more giving trust to the mathematics. Okay, some of the author giving the much more trust on the physical system. Okay, but mathematics and physical system both are important. Okay, both are important to understand, both are important to realize the problem. Okay, so both of the concept is necessary. Okay, that's why I am always suggesting you go through at least 3 book. Okay, for developing your better knowledge, better idea. Okay, so you can also follow some idea from Roshid books. Okay, in Roshid books the initial power electronics concept is given very good with having lot of mathematics, lot of things are there. Okay, but Roshid also very good book for power electronics converter, but especially for switch mode power converter you can follow that Erickson book and Ned Mohan book. The so Ned Mohan book, it is given that switch mode power supplies like that. Some chapters are there, 2, 3, 4 chapters are there. You can follow those chapters. Okay, so you can also get that idea. Okay. So I think all of you able to understand the changeover. That means how would I going getting that averaged equations of that inductor currents. Okay, that means that intermediate steps are given that computing that ideas that I am asking you for computing that equations in coming week by the coming week and show me and submit that one as a assignments. Okay, that computing everything that inductor response, inductor current response, capacitive voltage response for buck converter, boost converter. Okay, and the plottings are there with the changing of different variables. Okay, you can ask me. So I can also suggest something about it. Okay, so here you can compute that IDS. So final value of ITS is equal to the initial value of I0 plus the switching period of TS multiplied by the average slope, that is VLTS by L. Okay, I think you are getting that expression. How that expression is coming, that I have discussed. Tell me what you are asking.
Sir, in which software we need to simulate that
Which?
software, sir? That we
Okay, software you can use normally we are using MATLAB. Okay, so MATLAB is we are normally follow that MATLAB, but you can go for some of the open access software also, that Python like that way. Okay, Python is there, open access software, but you have to write the code. Okay, so in MATLAB also you have to write the code for expressions for getting that eigenvalue everything. Okay, so all the time drag and drop is not working for understand the for understand the simulation, sorry, understand the converter dynamics. So we have to calculate sometimes. So some portions you can follow MATLAB also. Okay, some portion is there in model, some portion you are written in code. Okay, means code in M5. Okay, you can fetch those values and you can plot those values. It is MATLAB is very useful and is very means what can I say, used to software for researchers. Okay, so you can follow the MATLAB, no problem. For computational analysis, you can follow the MATLAB, but you can also follow some open access for MATLAB software like Python. But in that case, totally you have to retain that equations. Okay, it is not so difficult one. Okay, you can write the equations in coding from also in Python platform. Okay, then you can simulate it and you can check that value. Okay, so there is no big problem. Okay, see, the computation and simulations means computation work normally done by the solver. Okay, that solver is MATLAB. Lot of solvers are there. The ODE, ordinary differential equations. Okay, so the solving of that ODE is most important thing. Basically, you have to find out that the roots of your system. No? So that's why it is important. Okay, so MATLAB you can also use. So Python you can also use. Python is open access. MATLAB is not open access, but it is accessible. You can install the MATLAB. It is available in our institute software vault. Okay, so you can go there. Computational what can I say, resources in NIT Rourkela. Make a Google search. Okay, you can get the software vault. You can talk to your seniors also, so you can get some vault, software vault in NIT Rourkela. So it is accessible from the internet. Okay, so you can download the software from there. Okay, so up to MATLAB 2014 it is available up to 2020. Okay, but you can use as per the compatible of your laptop. So 2014 you can also use, no problem. Okay, so it is which one is compatible with your system, so you can solve all those problem. Okay, no problem. And another thing you can do, it's that Ericsson and books having lot of exercise work. Okay, so side by side you should solve that exercise. Okay, so it is also one of your assignment. So you can I think you all of you in a single group. Okay, means we having the, you should have the group in your class. Okay, so you can solve means you can go for that group study. Okay, so some of the problem you can solve by yourself. Okay, some of the problem you are facing problem, in that case what you need to do, you can consult with your friend. Okay, so what is any of them is working on it or not. So finally all of you prepare one single assignment. Okay, and that single assignment should be submitted by your CR. Okay, that assignment having should contribute, that assignment having the contribution for the all the students. Okay, so they should write give their contribution and prepare one single assignment. Okay, and that will be compiled by your seer. Okay, it doesn't mean that every work done by the seer. I am not supposed to say like that way. Okay, so all of you should solve it for individual site somehow. Ericsson, that I have completed several chapters from the Ericsson book. Okay, so you can follow all those chapters, and you can follow all those chapters and try to solve the numerical problems from there, from the exercise. Okay, so then finally you are compiling. Okay, so some all of you try to complete by your side. Okay, so if you have any problem, any of the numerical problem, okay, in exercise, so you can consult with your friend. I think one of you are not you are facing problem, but one of your friend is able to solve this one. Okay, so all of you can make a group study like that way. Okay, so right now that's WhatsApp is there, MS Team is there, so there is no such problem for virtual meeting. Okay, also in Google Meet also be possible. Okay, so you can make a virtual meeting, share your slides, everything, and prepare one final file for that assignments of your Ericsson chapters. Okay, so that will be submitted from your end. So that the marks will be there, definitely the marks will be there, and individual submission is there for that computational analysis. Okay, so individually you can solve this problem. Again, it should not be like that. You can try it first your side for computation analysis. So if you have facing any problem, so you can discuss yourself. So always my agenda is like that, in not like only your class. In BTech classes I am always telling you that engineering syllabuses subjects, actually what we are doing here, that is a professional courses. Okay, so in professional courses one should help other. Okay, because we are working on a team. Okay, so I'm telling you, it's a teaching learning process, means sometimes I can also learn from my students. Okay, that students are definitely learning from the teacher. It doesn't mean it is not a irreversible process. Definitely it's a reversible process. Okay, so teachers sometimes also learning from the students. So in I am also taking some BTech classes, so where I know that they are very technically smart, that students. Okay, sometimes I can learn the smartness from their side. Okay, so what may be improvisations may be done by the softwares. Okay, so up to date idea also be required, no? So I can understand, I can also learn from their side also. Okay, it's not like that the students is learning from the teacher always. It's not like that. Definitely it is there, but teacher also learns sometimes from the students. So some of the teacher is admitting that points, some of not admitting, but I am very transparent with my students. I am very friendly with my students. Okay, so I don't have any problem for admitting that sometimes I also learn from the students. Okay, so definitely it is there. Let's say. Okay, so I think all of you able to understand my points and prepare that assignment. Okay, that I have covered from day one. Okay, so that Ericsson syllabus, Ericsson exercise, you have to solve it. Okay, and if you have any problems, so definitely you can discuss with your friend circle. Okay, and prepare one generalize. Okay, one generalize exercise copy. Okay, so that will be submitted. Okay, it may be soft copy, it may be, definitely it should be the soft copy. We find out a final PDF and share with me. Okay, so I will share, I will discuss the date. Okay, you should prepare it. So I will discuss I will collect it before the before just completion of my course. Okay, after just completion of my course I will give 7 days. Okay, so after that by the 7 days you have to submit that assignment, and side by side the small assignment, the class module submission, that will be going on. Okay, there will be no problem, but this assignment, the exercise from the Ericsson book, that is more important. Okay, all the portion having marks. Okay, don't be take it very easy. I mean simple, everything is simple, but don't take it is very casual. Okay, every point, every have we are having some TA marks, no? So it is segregated in several points. Okay, like your attendance, like your class performance. Attendance I can understand from that attendance sheet. Also I'm downloading the attendance sheet, okay, after the means duration of the class period. Then class performance will understand that that you have submitted regularly the class notes through Google form to me, okay, so that I can understand your class performance. Then class test will be there, okay, so class test that you have performed only already. I have taken one class test, okay. Then some assignment, that assignment I'm asking for, that assignment that next week you are going to be submit that computational assignment. Another main assignment that will be submitted by the just completing my syllabus. I have given some time, another 3-4 days, okay. So by this time you have to submit that final assignment, okay, like that way. So all the components having some marks for your TA, okay. So so I think till now I have discussed so much thing about your inductor current expressions over the switching period, okay. Then we should go for the capacitor waveform, okay. So similarly, like your inductor current, we can also go for that capacitor voltage and current waveform. I think this portion I will discuss in my next class, okay, so on tomorrow class. So that is enough for today. So if we give you more things, so it will make you jumble, okay. So my suggestions, you should go through that portions, okay, before attending my tomorrow's class, okay. So you can follow it any of the books, okay, like Erickson, maybe Nedmohan. So I am following that Erickson, so you can understand better, okay, so you can realize the thing better, okay. So till now I think this is enough for today's class. So in my